Good morning, my name is Minyu. I would like to present to you the work we have done in this paper. This work focuses on fault-tolerant task mapping problem and proposes a reliability of a fault-tolerant task mapping approach under several DVFS schemes. I will introduce these four parts. The continuously increasing application complexity requires high performance from the system. To meet these demands, multiple architectures are typically used. Energy consumption has also become an important concern, especially for systems with limited energy budget and due to green computing. In order to get the correct results, real-time applications require both timing guarantees and reliable execution. That is, tasks must be finished correctly and before their deadlines. However, due to the technology size reduction and the increasing scaling of CMOS technology, the system execution is not always idle, and thus fault can occur during the system execution. The faults are generally characterized as soft or transient faults and hard faults. Since transient faults happen more often in this work, we focus on the transient faults. The reliability of a task is defined as the probability of executing this task without error. It increases with frequency increasing. In order to enhance reliability, high frequency is assigned to execute tasks. Another way is to use fault tolerance techniques like task recovery and task replication. Overall, the solutions to enhance reliability increase energy consumption. Dynamic voltage and frequency scaling, short in DVFS, is a technique used to manage resources. The systems have been enhanced with DVFS, and by scaling down the supply frequency, energy consumption is reduced. But this has a negative impact on reliability enhancement. Therefore, efficient task mapping approaches are required in order to obtain low energy consumption and reliable real-time execution as well. In the literature, two popular problems are studied according to their objective. The first one is to maximize the reliability of all tasks, and the second one is to minimize the total energy consumption. Our work belongs to the second category. Considering fault-tolerant techniques, task recovery and task replication are commonly applied. Task recovery means that a task is re-executed when it's faulty. Task replication replicates full or partial tasks on different processes. It's very unlikely that all replicas fail. Based on the problem formulation and the solving method, the solutions are either feasible or optimal. Existing works have several limitations. For example, some approaches assign high frequencies to meet the reliability requirements. Such solutions increase energy consumption. It may also be impossible to satisfy reliability constraints even at high frequency. Other approaches apply full replication, leading to larger energy consumption due to the execution of multiple replicas, or partial replication without considering timing constraints. Our work combines the benefits of the aforementioned approaches to achieve energy reduction. Partial replication is applied only when the energy consumption is lower without violating timing and reliability constraints. The system model of this work is a parallel application consisting of several dependent tasks with individual deadlines. The multiple platform consists of homogeneous cores. We consider 3 DVFS schemes based on the frequency assignment, that is task level DVFS, where each task is assigned with one frequency. Processor level DVFS, where each processor is assigned with one frequency, and system level DVFS, where all processors in this system is assigned with one frequency. Obviously, the flexibility in frequency assignment among these 3 DVFS schemes decreases from task level to processor level and to system level DVFS. Here is our proposed approach. For more details, please refer to the paper. Here is an overview of the parameters and variables used in our formulation. I will not go in details in the mathematical formulation in this presentation. Please refer to the paper as well. This slide shows the final problem formulation on the task level DVFS. The main point we want to show here is that there is a nonlinear combination of variables, so the problem is formulated as a mixed integer nonlinear programming, short in MINLP problem. We apply a mathematical method based on replacement to safely and equivalently transfer it into an MILP problem form, which is linear. Considering the experimental setup, we assume a platform where each core has 6 frequency voltage levels. For the benchmarks, the worst-case equation cycle is selected randomly in a range which is obtained through measurements of some mid-bench benchmarks on a RISC-V core. By adjusting the value of k, we can range the value of deadline from tight ones to more relaxed ones. To show how reliability requirement influence the behavior, we perform 2 setups, one with relaxed requirements and one with more severe ones. All experiments are done with Groovy solver. In this presentation, we will present experimental results for 4 cores and 20 tasks. For the rest of the experiments, you can refer to the paper as well. The proposed approach is compared to 2 recent approaches, the reliability-aware mapping approach and the duplication mapping approach. I will explain the evaluation from these parts. These tables give the energy consumption gains of IM and TDM compared to our approach. For IM, we observe a minimum gain of 0 except a small gain in task level DVFS. This happened in strict deadlines where our approach and IM have a similar behavior, both applying a high frequency to meet the timing constraint. With deadline relaxing, our approach starts to perform partial duplication to save energy, which enlarges the energy consumption gain on average. In system-level DVFS, the average energy consumption gain reaches the highest. This is because the system-level DVFS has the lowest flexibility in frequency assignment, so IM needs to select a high frequency in order to meet the highest reliability threshold among all tasks and execute all tasks with this high frequency. This causes large energy consumption. At strict deadlines, TDM consumes much more energy than our approach to do duplication for all tasks if solution exists, while our approach can use a proper high frequency to execute only original tasks. When deadline is more relaxed, our approach performs duplication for all tasks, same like TDM, which can be seen that the energy consumption stays zero. Generally, considering our approach consumes the least energy. For each approach, the feasibility stays the same among the three DVFS schemes. In this experimental setup, our approach and IM have the same feasibility since the reliability constraints can always be met by executing only the original task with a high frequency. Compared to TDM, our approach is able to find solutions in significantly more experiments. This is because our approach is not obligated to duplicate tasks if this original task extreme is reliable, while in TDM all tasks are duplicated. When the deadline becomes relaxed enough, our approach has a similar behavior like TDM since it decides to duplicate the majority of the tasks. Both approaches achieving 100% in finding solutions. In general, the proposed approach and IM find more solutions than TDM. Generally observed for all DVFS schemes, with deadline relaxing, more tasks can be duplicated by our approach due to the available time slot. There are two interesting observations here. For some points, the duplication percentage decreases when deadline is relaxed, and not 100% duplication for all tasks on the task level and process level DVFS. The reason is that different DVFS schemes have different flexibility as explained above. When the task's reliability requirement can be satisfied without duplication and at the same time energy consumption is less than the energy consumption when duplicating with the lowest frequency. In this case, task level DVFS and process level DVFS do not duplicate this task. But with system level DVFS, the same frequency is assigned to duplicate all tasks. As a result, duplication do not provide benefits even if time slot exists. In this experimental setup, we explore how the fault mode influences the ability of obtaining solutions on the task level DVFS. The results show that our approach provides better results than IM with lambda 0 increasing. The ability of IM to always find a frequency to meet a reliability requirement decreases, especially for tasks with high reliability requirements. Since with lambda 0 increasing, the reliability decreases at same frequency. Our approach is able to still meet these high reliability requirements by duplicating tasks and assign a high frequency. Here is the energy consumption of IM compared to our approach in civil setup. With lambda 0 increasing, the process sensibility to fault is increased. the energy consumption gain are slightly reduced since our approach also needs to select a high frequency in order to meet the high reliability threshold of tasks. There is an abnormal case here. This is due to a solution found by our approach, but not by IM. Here is a brief summary of our work. One of the limitations is that due to the complexity and computation time, the optimal solution is time-consuming. As a diversion for future work, there are some interesting points here. The system model can be extended, for example, to heterogeneous cores, and task communication cost can be considered as well. For replication policy, duplication can be extended to several replicas for one task, and the degree of replication for each task is to be decided. To achieve less computation work and also keep near optimal solution, heuristic methods are worthy to be considered as well. Thanks for your attention. If you have any questions, please don't hesitate to contact us.